It's 5 minutes past it already. Let's get started. In the last class, on Monday, we stopped at this problem where we tried to consider 3-point charges as shown in the diagram and as described in the text. And we were also, the question says that we should find the resultant force exerted on Q3. The resultant force exerted on Q3 is the force that Q1 is exerting on Q3 and the force that Q2 is exerting on Q3. So the force being exerted on Q3, we've described it as F3. The force that Q1 is exerting on Q3 is described as F13, while the force that Q2 is exerting on Q3 is described as F23. So we need to determine what is F13 and what is F23, and we have to determine them as vectors. So before we do that, I would like to just show a simple analogy. Let's say this is my graph sheet. This is y-axis, and this is x-axis. And this is the origin. Let's say this is 3. And this is 1. I'm sure this is familiar. If it's not familiar, then we are in trouble. Imagine I start from the origin and I start from the origin and I walk 4, let's say it's in meter, let's meter, and I walk 4 meters in the x direction, and I walk 3 meters in the y direction. A question you may want to ask is that, how far have I traveled? What is my displacement? And the simple answer to that is to say that since I traveled in this direction, then I moved up in this direction, then I must have, the resultant is that I had traveled from the origin to this particular point, let me call it point B. So I've traveled from the origin O to point B. And if you want to calculate how far have I traveled, a simple thing to do is to calculate the length of this line from O to B. And how do you do that? You treat it as a right angle triangle. And treating it as a right angle triangle, treating it as a right angle triangle means that we can apply hypotenuse or Pythagoras theorem to determine the length of the hypotenuse. Since we know this of the origin to the length 4 to be 4 meters, so to be 4 meters, and the height here to be 3. We can use Pythagoras theorem to say that OB squared is equal to 3 squared plus 4 squared, and we end up doing them up to say this 9 plus 16 and say that's 25. Then OB will be a square root of 25, and that will be 5 meters. So we can determine this to be the length 5 meters. So if the question is that I traveled to the right 4 meters and I traveled up 3 meters, what is my displacement? If you say 5 meters, you have only said the resultant of the displacement. If you say displacement is not the same as distance. Displacement is a vector quantity. You describe it in terms of magnitude and direction. So the magnitude here is 5 meters, but in what direction? Is when you specify the magnitude and the direction, that is when you have actually describe displacement. So a good way to describe the displacement would be that you say, since I travel to the right in 4 meters, so we can use a unit vector. Let's use a unit vector to say that the unit vector r caret to mean that I travel to the right in 4 meters. So I can say that is 4 x caret. I traveled upward in 3 meters, that is 3 y caret. So in vector representation, 4x plus 3y, the resultant is 5. So, but since we are talking about a unit vector is a vector whose magnitude is equal to 1. Unit means 1. The magnitude is 1, and a way to make the magnitude to be 1 is to divide this 4x plus 3y by the resultant of 4x plus 3y, which is 5. So it's just like I'm dividing 5 by 5, which will give me 1, the unit vector. So in the unit, so to a simple way to now go about this is to say that 4x plus 5y, we can divide by 5. It's as good as 0.8x plus 0.6y. So 0.8x plus 0.6y, that is the unit vector. So if you try saying you want to find the resultant of 0.8x and 0.6y, you would get 1. So you can do that in your leisure time. So, but what I'm trying to achieve here is that if I'm to now describe the displacement from 0 to b, I can say traveled 5 meters, but in what direction? 5 meters in 0.8x caret. Sorry, 0.8x caret plus 0.6y caret. So 0.8x caret plus 0.6y caret has a magnitude of 1. When you multiply 5 by 1, you still have 5. So you have not committed any crime by multiplying 0.8x plus 0.6y caret, multiplying it with 5. So it's still 5 because it's 0.8x plus 0.6y is 1. So if you decide to expand this equation, 5 times 0.8x, that should be 4x, right? 5 times 8, 40, 4. Yes, 4x caret. Let's say 4.0x caret plus 5 times 6, also 3y caret. So if you do that, just like where we started from, you still have a magnitude of 5. And so a way to describe the unit vector, is to talk about the magnitude. This way to describe a vector rather is to talk about it in terms of the magnitude and the direction. Okay. Some other ways we can describe it in some other ways. We can decide to say, okay, let's say, since we said 5 into brackets 0.8x plus 0.6y. Conventionally, it's more convenient to instead of saying x caret, most times you say I, instead of saying y caret, usually called j. So I, if it's a 3 dimensions, we say I, j, k. So I, j, and k, they only show us that they are pointing in x, y, or z direction. So it's just convention to call them in terms of the unit vectors or in terms of the direction I, j, and k. Okay. Then the next way we can, another way to describe that same vector, since we describe something of this nature, 4, 3, call this 5. Another way to describe this vector since we know the magnitude to be 5, we can also just talk about the angle. If I know the magnitude to be 5 and I know the angle to be theta, then I can say that I have described the vector by specifying the magnitude and its direction. So specify the magnitude and the direction means I am describing a vector. So how do we, what is theta? You can get it in several ways. You can use sine theta to be equal to 3/5. If you decide to use cos theta, that should be 4/5, or tan theta, which is 3/4. So we should not go back to that so that I will not be embarrassing you with basic mathematics and the likes. So let's move straight to our business, which is, I have tried to show you in simple terms, we all walk all around. So displacements should not be something that would we cannot relate with. But electric field, we have not seen the electron with our naked eyes, but we can feel the presence. The presence have been measured, they've been quantified. So that is the reason why, in this case, we have described F3 to be an addition of F1(3) and F2(3). And what is F1(3)? F1(3) is the force that Q1 is exerting on Q3. And we defined F1(3) to be Q1, Q3 over R13. And the major question is, what is R13? R13 is a unit vector, which we can define because in this scenario, we expect F1 to push F3 in this direction. So since it's pushing F3 in this direction, it still aligns with this straight line. Come on, pointer, where you come out? Oh, come on, get back. Oh, sorry. Come on. Well, I'm trying to bring out the pointer, but it said, no way. Let's see who wins. Okay, good. So if you look at this line, like we've established in the previous lecture, that the force acts on a straight line. So Q1 will push 3 away, still on this line, which continues with this blue arrow. Then what is the force? The force has been described as KQ1 Q3 over R13 times R caret. R13 caret is a unit vector. It has a magnitude of 1. Multiplying 1 with any particular value makes no difference. So how do we define R13? It's as good as looking at this place and now treating this. So we have to use our intuition to bring out a triangle here. And by doing that, we can now describe, like the way I did in the analogy just now, to say that from Q1 to this point has a length A, and this point upward also has a length A. So I can come to say that my R13, and what is length A? Length A is defined there as 0.1 meter. And that means that my R13 will be, R13 caret will be defined as 0.1 meter in the X direction plus 0.1 meter in the Y direction. So let me remove this. And this. Sorry. Then divided by the magnitude. The magnitude, what we have just said is that Q1 to Q3 means a force which Q1 is exerting on Q3, and the direction is in 0.1 meter to the right, 0.1 meter upward, and the resultant will point in the direction of this blue arrow. And when that is, and a way to describe that effectively is to talk about the R12 caret. And so the direction can be defined as 0.1 meter to the right plus 0.1 meter upward divided by the magnitude. And the magnitude here is 2a. Defined in the last class is 0.1414 meter. So we can come here to say divided by 0.1414 meter. So meter will cancel meter. So that confirms that we are dealing with a unit vector, a unit which is 1. Unit vector has no units. It is unitless and it has a magnitude of 1. So multiplying 1 with with your magnitude makes no difference in terms of the magnitude, but gives us additional information about the direction. Okay, so when you calculate when you divide 0.1 by 0.1414 and you add it to the other 0.1 by 0.414, what I'm trying to say in English or in mathematics is 0.1 divided by 0.1414 x caret plus 0.1 divided by 0.1414 y caret. If you do this at home, I try to find, okay, you are at home anyway. If you did this at a leisure time, I try to find the magnitude. You should have a value of 1. So everything I have here, if I simplify, and even if I don't bother to simplify, I can use it to replace this R13, and I will be describing the magnitude and direction of the force of F1, or the force of Q1 on Q3, which is F13. So the other question is saying that what is F23? It's not the other question. The other part of the question is saying what is F23? And if you look at F23, let me get another color. Let's say color green. Q2 is attracting Q3 in the negative x direction. Q2 is exerting a force on Q3. It is attracting it. It is attracting it to the left. It's exerting a force on it to the left towards the negative x direction. And what that means is that to determine F23, let me get a new slide in there. I was trying to get to Mr. Okay, I think I can just bring out the screen here. And if it's, let me get to F3. Focus. Okay. Sorry, I was trying to get a fresh screen so that we'll talk about F23. So let's talk about F23. Yeah? F23. F23 can be described as the constants Q2, Q3 divided by R23 squared times the unit vector R23 carats. So this should be standby on our at one side of memory, so we should keep that in mind. So the question should now be, okay, let me write it here, F23. Is equal to K Q2 Q3 over R23 squared R23 carats. So we know, just like we did in the previous first part. Sorry, I forgot to put squared. Yes, sorry, there should be squared. Yes. So, and that's so we are interested in K2, Q2 and Q3, and Q2 is 2 microcoulomb. So we don't really need to bother ourselves with the sign. We can just come here to say that after K, we say 2 times 10 raised to the power minus 6. We don't really need to specify minus 2 right here. We are interested in the magnitude at this corner. While Q3 is 5 microcoulomb, which is 5 times 10 raised to the power minus 6, divided by what is the distance of separation between Q2 and Q3? That is 0.1 meter. So the next thing to do here is to say 0.1 squared. I don't need a bracket here, but since I've written 0.1 squared. So everything we have here is will give us the value of the force in Newton, the magnitude of the force. Then in what direction? The direction is, let's come back here to look at in what direction. This is very straightforward. We should have even started with this. The direction is, this is the Q2, which is acting on Q3. So Q2 here is the chairman of this area, is the landlord here. And it's attracting Q3 towards it. This is attracting Q3 towards it. Then the force acting on Q3 will be acting in the negative X direction. If it's acting in the negative X direction, you don't have to waste our time doing any story down to just say that this is acting in the negative X direction. And you can just say, let's just take one corner of the screen and say, come on here, come on. One corner of the screen and say our R23 carats is equal to minus X direction, minus X carats. So if we were to be using the IJK as our for our notation, then you just say minus I. So instead of, so this will come here to mean minus X caret. So when you expand this and you multiply it out, whatsoever you get, will describe the magnitude and the direction. So the force that F23, the force F23, which means the force that Q3 is exerting on Q3 as this magnitude and this direction. And by specifying that, we have described the vector. So let's move on to conclude the question. The question did not say what is the force of Q1 acting on Q3 or Q2 acting on Q3. The force is, it's not saying what is Q1 acting on Q3 or Q2 acting. It's saying what is the force of that is acting on Q3. So we are the ones that looked at the diagram and noticed that there are two charges nearby, and we have considered the force of Q1 acting on Q3 and also Q2 acting on Q3. And since we have written them as vectors, then we can add them up easily, like simple addition. We can add them up easily. If we know F13 and we know F23, then we add them together to give us F3. So you have to remember that F3 is equal to F13, that is the force of 1 acting on 3, and F23, the force of Q2 acting on Q3. Okay. Acting on Q3. So, and that will be equal to. So when you take this, if you look at F23, it's given in terms of X caret. When you look at F13, it's given in terms of X caret and Y caret. So you expand, you add the X, the like times together, just like you are asked to add. So the question here is like saying you should add 3X plus 4Y. You should add it to 2X. The answer is 5X plus 4Y. So I expect it to add the initial time to add to obtained your F13 by bringing R13 into F13. Then the next thing is when you expand, you add the values of X in F13 to the values of X in F23. And for Y in this problem, F2 is not exerting any force on the Y direction on X3. The force it's exerting on X3 is only in the X direction, to be precise, in the negative X direction. Unlike F1, which is applying a force that has both X components and Y components. So you can easily add them together in terms of X and Y, and at the end, you would have a F3 that is having certain values X prime plus certain values Y prime, all Newton. And the next thing you do is to find the resultant. So to finding the resultant of to find the resultant of a vector, I think you've done that in last semester. And that reminds me from about 9:30 a.m. today, your physics 102 and 103 scores will be listed. So if you have, so you can just come and look at it when you resume physically. Okay, if we find, I'm looking at the charts, if we find the resultant force between two charges, to we add F21. and plus F12. Okay, so there is a question here that says, if we find the resultant force between two charges, do we add F12 plus F21? I think this question is not direct. It's not, I can't really get it. But if you say F12, you are talking about, according to our convention, we are talking about the force that Q1 is exerting on Q2. And if you say F21, we're talking about the force that Q2 is exerting on Q1. So when you add them together, it should give you 0, because these two forces are acting in opposite direction and they have the same magnitude. So they should add up to 0. Let me see if there's another question there. Can you explain R13 carets? I really don't understand. Maybe the question was like it's the long bit before I explained it. Can you explain? Can I scroll down? Can you explain the vector components again? Oh, sorry, we need to move forward. I'm sorry. Every other question can be solved by you working on your own. Physics does not end in the class. You need to do additional work on your own. So let's talk about electric field. We've spoken about electric force and electric field. Fine, we have an idea of what electric phenomena is. And the field, I will say field, whatsoever the field, it's a region. The field is a region. So similarly to electric field, it's a region where electric force is felt. So for us to have electric field, we should have electric charges. So for an electric field to exist, we should have at least an electric charge. And if it's, and we know the properties of charges. Okay, so when we have a certain charge, we should, let's say a positive charge, we should experience field around this. And so this should be familiar to you. So when we have a certain electric charge, let's call it Q1, and we have another certain electric charge, let's call it positive again, let's call it Q0. For the fact that we have brought one electric, so let's assume Q1 is the charge of interest to us. Now we brought another Q0 close to it. Q0 will experience a force due to the presence of Q1. Fine, we've spoken about that before, Coulomb's law and the likes. But now we are interested in just Q1. That when we bring a certain charge into the region, to the electric region of Q1, if we bring another charge, such like Q0, into the region of Q1, how strong is it going to feel the presence of Q1? So that is what electric field tells us. And to be precise, we say electric field strength. So how strong is Q1? How strong does Q1 attract or repel other charges? And that leads us to defining electric field strength. So a simple way is to say the force, which we've defined before. In this case, the force which we've defined before is equal to F equal to K. In this case, you'll be saying Q1, Q0, divided by the distance of separation between them, R squared. Sorry, not distance of separation, square of distance of separation between them. This is the force of attraction. Now we are interested in the electric field strength of Q1. And a simple way to go about it is to say F divided by that charge that you have brought in, the force of attraction divided by that charge that you have introduced. That defines our electric field strength. So it's the force of attraction or repulsion, 20 charges, divided by Q naught. Q naught here is the guest. In this case, we call it the test charge. So electric, just like force, electric field strength or electric field is also a vector quantity. So we define the electric field also in terms of magnitude and direction. And not just that, one of the advantages of describing electric field in terms of magnitude and direction is that we can add them up easily. They can cancel out. If I say a force of 10 Newton is acting to the right, another force of 10 Newtons is acting to the left, easily you can add it up to say that the resultant force is 0. So just like vector quantities, they add up. Electric field adds up. So the electric field from a particular charged body adds up to the electric field on another charged body, and we can always determine the resultant electric field. So, like displacement, when you leave your room, let's say in Z-call, you go to the cafeteria, you leave the cafeteria to the classroom, you leave the classroom back to your room, and you now ask yourself, what is my displacement? Your displacement is 0 because you have returned to where you started. The displacement is 0. So the same way in electric field, we can add up going to the left to going to the right, algebraic. So what I've just said is defined over here to say that the electric field is the force divided by the charge, the test charge. And that is defined in terms of the unit is Newton per Coulomb. Newton is for force and Coulomb is for charge. Since we are dividing force by dividing force with charge, then we can easily say that because we are dividing force with charge, we can easily say that we are dividing Newton by Coulomb. So a simple formula to describe electric field, just like we have, if we are conversant with the, by now, we should be conversant with the formula for electric force, which is directly from Coulomb's law, to be Q naught over 4 pi epsilon naught R squared, or you say KQ Q naught over R squared. We can bring out the value an expression for electric field by dividing F with Q naught, and we have these beautiful expressions down here. So you can see it looks just like a force, but the difference is that instead of having 2 Q's as a numerator, we're having a single one. And that single one is telling us the strength of that certain charge. So looking at it, the strength of a particular charge is directly proportional to the magnitude of the charge and inversely proportional to the square of the distance you are taking your measurement away from that charge. So when you are moving closer to a particular, when you are in an electric field and you are moving towards a charge, let me say not you now, a charge body is an electric field and it's moving towards a charge, the force that it will experience will increase as it moves closer to the charge. And it's not a linear relationship. We should see the R square. R square is not R. R and R square, they are not weights. So it's not a linear relationship, it's square relationship. So moving away from a charge, just like I showed here, moving away from this charge, moving away, the strength of this central charge reduces with a square, inverse square, reduces with a square relationship as you move away. So as you move away, the strength that is felt as the result of the presence of this charge drops rapidly when you move away. And when you move closer, it increases rapidly. Also, this particular charge, its magnitude also determines the strength. So the larger the magnitude, the larger the strength that is experienced. So let's move. So a qualitative and okay, you still have this data to read. Okay, so when we're talking about electric field, just like I've tried to describe here, we describe electric field with lines, and those lines have rules. They don't intersect each other. If it's a positive charge, if it's a positive charge, the lines radiate outward. The arrows point outwards if it's a positive charge. And if it's a negative charge, the lines point inwards. So that's one of the rules. The lines, they don't intersect, will be seen some them. So all the stories I have here, I think they are still ahead with some diagrams. And if you look at this, it's just like you having a small bulb, and you have a small bulb, and you open your eye halfway, you see some tiny lines that move out of that bulb. Those tiny lines can mimic the electric field. Fine, I'm drawing this on a paper, but in reality, you have to picture it as something that is radiating out in all directions, just like your bulb, as rays of light emanate from your bulb. So also you can imagine the field lines emanating from a charged body. So when you move closer to the bulb, you are going to intersect so many lines. You are going to intersect so many ray lines. But when you are far away, with maybe with the tip of your finger, the lines that will cut through your finger will be so small compared to when you move closer to the bulb. So the number of lines that cut through a certain surface also gives us information about the strength that is felt at that point. So the strength of field is not just measured based on the magnitude of the charge, it's measured based on the distance you are away from the charge. So the lines of force, they are not things that should be seen, they are imaginary lines. They are not things you see, but they help us to understand electric field better. So like I said that electric fields are vector quantities, so that is why we can add them up. According to this expression, we can add them up like forces. You cannot just add forces together, except you have described them in terms of magnitude and direction. Because when you specify just forces and you just add them together, if you just add the force pointing upwards to the one pointing to the right, you just add them up, you must have committed a blunder. So when there are ways with which vector addition, which I expect you to have done in last semester, those are the method applied in last semester is also what is applied in all around the fields of physics, as long as it's a vector quantity and you have described them in terms of quantity and direction, you can add them up. So similarly, the electric field as well. So when you have so many charges, you've determined their field strength in terms of magnitude and direction, you can add them up and determine the electric field strength at a particular point based on the presence of several charges surrounding that certain point. So we have some rules here that says the properties of field lines, they start from positive charges and end in negative charges. It may start from positive charge and end at infinity. It may start from infinity and end in the negative charge. Lines of force never cross, they don't intersect. The direction of field at a point along the tangent of the line, the direction of the field at a point is along the tangent to the line, of course. At location where electric field lines meet the surface of conducting bodies, the lines are perpendicular to the surface. So I'm not really talking in terms of equations. These are things that interest me, diagrams, but when you get this slide, you should take your time and read if you like the storytelling, but everything written here in English, I've described in physics and mathematics. So, like I was saying before that, let's imagine you have a bulb. Let's imagine you have a bulb and there are the rays of light have come out of the bulb. If you come with a small piece of paper of certain area A, when you move the paper having area A close close to the bulb, when you move the paper close to the bulb, as you are moving closer, you would notice that the number of lines that is crossing the paper will increase as the paper is moving close to the bulb. The number of lines or the number of ray lines intersecting the paper will increase as the paper moves close to the bulb. So that is something you must have observed consciously or subconsciously. And that takes us to what we define as electric flux. Electric flux described as phi. So the number of lines or electric field is related to the electric flux. So the number of lines crossing that paper, I can call it flux. So if I have a unit area, I can count the number of lines and say that the flux is increasing or reducing based on the location from the charge. Sorry. So anyway, we would see some diagrams that show us better. So the flux divided by area gives us information about the electric field, and and flux can be, which is phi, can be defined as the charge over epsilon. The epsilon which is the permittivity of the particular material. In Coulomb's law, we have epsilon naught, which is permittivity of free space. Free space is just like a vacuum. It's vacuum, but now we are just like vacuum. But permittivity, there are different materials. Epsilon naught talks about that of free space, but permittivity, different materials have different electric permittivity. So that's okay. So like I've said earlier, a positive charge can be described, or the field lines around a positive and isolated positive charge can be shown to emanate from the center and emanate radially outwards, while the field lines of a negative charge can be shown to be emanating from outside, from infinity, from where we don't know, terminating inside the negative charge. So the positive charge is just like a source beaming out, while the negative charge is like a sink draining everything. So one is spending, the other is receiving. So when we have two like charges. This is a negative charge. You can see the lines are pointing inwards. Another negative charge, lines are pointing inwards. And one of the rules is that they will not intersect. Instead of, if not for the presence of this charge, you would have these lines that were bending in this direction would have come towards the left. But because of this negative charge, they need to bend so that because they should not intersect. And because they are opposite charges, they are both sinks. They are both looking for lines that will come and crash into them. For that reason, they would not really interact. They'll be pushing themselves away. Their field lines will not originate from one and terminate in the other because they are like charges. But what happens if they are opposite charges? Just like we have in this diagram, you can see that the positive charge is still having the lines radiating outwards, while that of the negative charge is still coming inwards. But in this case, you can see that the line from the positive charge is originating from positive charge and terminating in negative charge. So they are unlike charges, and this is expected. So, and also I forgot to mention, the lines of force tells us the direction that a positive charge will move. So in this case, when you put a positive charge here, it will move away in this direction. When you put a positive charge here, it will move towards the negative charge. So the arrows on the lines of force gives us information about the direction where a positive charge will move when placed at that particular point. So if you put a positive charge here, ideally, it will not move because it is not experiencing any force there. There are no lines there. And when in this scenario, you would expect the positive charge to move in this direction and all around. So in this diagram, they show two equal and opposite charges, but in this diagram, it's showing